All right, so the next topic is using root locus to design PID controllers. PID controllers are very important in industry. They have a lot of applications, and we want to use root locus to design these PID controllers. Uh, Clearly, if I want to use root locus, it means that I have access to what root locus needs. So the ingredients of root locus, which are poles and zeros of the system. So the assumption here is that I have access to my system's transfer function. Therefore, I can locate poles and zeros of my system. And with the help of root locus of the system, I can design a PID controller. So a PID controller can be written as equation 1. The transfer function of a PID controller has a proportional gain, it has a integral gain and a derivative gain. The derivative gain is being multiplied by the derivative term. The integral gain is being multiplied to the integral or integrator term 1 over s. And then the proportional gain is just being multiplied directly to whatever input we have. That's why it's called proportional gain. It's proportionate. So the output of it is proportionate to the input. If we do some math, we can write equation 1 as equation 3. What this means is that a PID controller by itself as a system is a transfer function with a pole and two zeros. So I have a system, it doesn't work well, I want to change its behavior, therefore I introduce a controller to it. Now this controller itself is a system. It has a transfer function that has two zeros and one pole. So this means that a PID controller introduces a transfer function with a pole at the origin as well as two zeros which can be located anywhere. So it's the degree of freedom of the designer, of the control engineer. I can place Z1 and Z2 where I want, and then based on that, the PID controller's behavior changes. So with adding these zeros and the pole at the origin, we can change the behavior of the system the way we want. So let's see an example. Consider figure 1. I have a second order system which is given with equation 4, and I have unit feedback, and what is desired is to change the behavior of the system. Now, what do we want to do? So first, let's look at the system that we have in hand. So G with unit feedback. This is the root locus of it. It has two poles at -2 and -3. And therefore, there is an asymptote here at -2.5. And this means that with the gain of 10, with k equals to 10, we have the percentage overshoot equal to 8.08%, and settling time is 1.5 seconds. Okay, so if the gain, if there's a k here, a gain here, and the value of it is 10, then I have this performance. Settling time, so the speed of the system is 1.5, and percentage overshoot, which represents the oscillations of the system, are 8.08%. Okay. Now, let's add a PID controller as figure 3, so here, with the structure that we talked about before. So I want to place a PID controller here that has two zeros that I want to design, and a pole at the origin. If I place the zeros to be at -3 plus minus J1, then the root locus would look like equation 4. So figure 4. So I had these two poles. Now, sorry, I had these two poles. Now I have an additional system being added. I know the pole of that additional system is at the origin. I place the zeros here. Now I want to see how this is going to change the performance of my system. If the zeros are selected at -3 plus minus J1, the root locus would look like the figure I just showed you. This means that if the gain is the same number, 10, percentage overshoot goes down, which is a good thing, right? We want the percentage overshoot to go down. And settling time goes down too. So it is desired too. So if a shorter settling time is desired, we can select zeros to be farther to the left. What that means is that with adding this pole and these two zeros, I increased the performance of the system. I made settling time shorter, which is what I want, and at the same time, I pushed down the overshoot, which is what I want. So the PID, the controller was designed in a way that it increased the performance or improved the performance of the system. Okay, so what's the procedure to design a PID controller? In the example of previous page, I just myself designed the PID controller and I showed you the effect of it to show you how good it can be. What's the procedure? So the procedure to design a PID controller is this. We need to define, or we need to determine the values of three gains that PID controller has, KP, KI, and KD, the three knobs that the design engineer has. So one approach that is discussed before is to use Ziegler-Nichols tuning method. So Ziegler-Nichols, as you know, is a table. We have Ziegler-Nichols table, and based on what we want to design, is it a PI controller, is it a PD controller, is it a PID controller? It tells us how to follow the procedure, and based on the gains we find, we design a PID controller. But another tuning method is the manual PID tuning, where the PID control gain can be found using trial and error. That has minimal analytics, and if you don't have transfer functions, that is desired. So both of these methods can be done if we don't have the transfer function of the system. So in the manually tuning PID, to manually tune PID controller, this is what we do. First, we set Ki and Kd equal to 0. Okay, so first, the only degree of freedom that is on is Kp. We gradually start increasing, start cranking up Kp until the output of the closed loop system starts oscillating. So we are trying to only use the proportional gain until we get to the edge of instability. After we found that Kp, we find the quarter amplitude decay. Okay, so what does that mean? It means that we want to decrease Kp to get to the point that the amplitude of the closed loop response reduces approximately to 1/4 of the maximum value in each period. We are going to see that in the next slide. So we first turn off Ki and Kd, crank up Kp until we get to the edge of instability. When we found that Kp, we decrease our Kp until we get this behavior. The behavior is that in one period of the oscillation of the wave or of the response, we have the closed loop response reduces approximately to 1/4 of the maximum value. Now, a rule of thumb is that you don't need to actually start decreasing KP from what you found. A rule of thumb is that start reducing it by 1/2. So we kind of know that it should be around 1/2 of KP. Then after you found this quarter amplitude decay gain, then increase Ki and Kd manually to achieve the desired step response. Example, I have a unit feedback system, negative feedback, and this is G. And root locus of it is this. So this is the behavior of the system I have already in hand. If I set Ki and Kd equal to 0 and increase Kp, so crank up Kp, as you know, these three poles start moving. This pole goes to the left. These two poles move towards each other and meet each other at this point, and then they leave the real axis. And then at some point, if I keep cranking up Kp, if I keep increasing Kp, they are going to cross the j omega axis. That's the point that we are interested in. That Kp for this specific system is 885.5. For Kp equals to 885.5, we get an oscillatory behavior similar to this. Okay, so I gradually increase Kp and I end up having this behavior. It just has pure oscillations. Okay, so that's the edge of instability. Now, when I find that value of Kp, now I want to find the value that gives me what we call quarter amplitude decay behavior. The value for this example is 370. So if we start searching, we find 370 as Kp gives us the quarter amplitude decay. Now, what does that look like? Let's see figure 7. This is quarter amplitude decay. So the maximum point here is 1.4, right? 1.47. If you subtract that point from 1, you get 0.47, right? Now, what I want to happen is that in one period, so one period of a wave is either from this point to this point, right? This is one period of the wave. Or alternatively, a period of a wave is from the peak to the next peak, okay? So what I want to happen is that in one peak, I want the wave to decay to a quarter of its value. You might say, wait a second, I have 1.26. 1.26 is not a quarter of 1.47. No, it's not. But if you just look at the portion that is above 1, so this is 0.47. A quarter, let's say 48. A quarter of 48 is what? Is 12. So now my wave is losing 3/4 of its value in one period. So that's what I want. So I decrease Kp so that until I get to a point that I have this behavior. After that, now I can use Ki and Kd to find the behavior I want.